the second part of the course, which looks at very similar kind of dynamical systems that we've been looking at, but from a not so much a topological point of view, but the point of view, a probabilistic or a statistical point of view. Okay. So the first thing we need to do is a little review of measure theory, which hopefully is just a review for you, but I just want to make sure that we all have a clear picture. You know, I will not go into very technical detail, but I just want to review the fundamentals of what a measure is. So do you know what the definition of a general probability measure is? Have you done this?
Yes.
You did this in the course here? No, you've done it before. No, you've not done that. Okay. Let's just go through quickly then. So we have a space. X is some set. And we have A is a collection of sets called the sigma algebra of subsets of X. What are the properties of a sigma algebra? You all know the properties is intersection, union, countable intersection, countable union, okay. And then we have a function from the sigma algebra to let's say 0, 1, okay, is a probability measure. Okay, if it is the fundamental property is that it's countably additive, right? So if A1, so if A1, A2, A3, and so on in A are disjoint, okay, then this implies that the measure of the union of AI, so the union, because it's a sigma algebra, then the countable union belongs to the sigma algebra itself, and this is exactly equal to the sum of the union. Okay, and then some of the details, like the measure of the empty set is 0, the measure of the whole set is 1, okay, but the fundamental property is this one, which is called countable additivity. So what is an example of what is the easiest example, or the kind of one example of the sigma algebra of subsets? Sorry? Exactly, the collection of all subsets. Okay? Now, unfortunately, it is generally not possible to define a measure on the set of all subsets. Have you done this? Have you studied this? You know this, yeah? Can you give me an example why it's not possible?
The big measure.
The big measure?
Has audiences and non-measurable set.
And what's this non-measurable set?
Looks like it's the equivalence classes of it looks like rotation,
we use the axiom of choice and we construct it.
Use the axiom of choice to construct it. Okay, so we'll not go through it, but I think that's there's a very nice, using the dynamics that we've got, there's a very nice way to construct such an example. If you take, in fact, a circle and you take the rotation and some irrational rotation, right? And then if you remember, what is the property of irrational rotation? So if you take a point x here, then the full orbit of x, which is equal to the set of points fn of x for n in z, all forward and backward exits.
Yes.
This is dense, but most importantly, it's an infinite orbit, right? It's not a periodic orbit for every point. Okay? And of course, any two orbits are either the same orbit or disjoint, right? If you take y So if x is different from y, then either the orbit of x is equal to the orbit of y, or the orbit of x do not intersect. You agree with this? Yeah? Because of course, this point, you look at all the forward images and all the backward images. If you take a point that is on the orbit, then its own orbit would be exactly the same. You just take a different starting point. You take all the forward image, all the backward image, it's exactly the same orbit. So any two orbits, if you take 2 points x and y, either the full orbit of x is equal to the full orbit of y, so they're on inside each orbit, or they're disjoint sets. Okay? Now, using the axiom of choice, you can say you can define a set, let E, okay, in S1 be a set that contains exactly 1 point from each orbit. Because there's an uncountable number of orbits. Is that clear? There's an uncountable number of orbits because each orbit is countable, and so there's an uncountable number, right? And so the question is, what is the measure of the set E? Okay, so that's the problem. We don't know. So if you could define the measure of E, we have that the measure of E. So you take we want the measure of the sum. Okay, wait. So the first observation is that then Lebesgue measure of Fn of E is equal to Lebesgue measure of E for all n in Z. Why is that? That's right, because it's a translation. And Lebesgue measure is invariant by translation. If you take any set and you translate it, then the measure does not change. Right? And therefore, we have that the Lebesgue measure of the sum of all n in Z of Fn is E. What is this Lebesgue measure? Well, what is this set here? This is the whole circle. This is everything, right? Because E contains exactly 1 point from each orbit, right? And so now you take that point and you take the whole orbit. This is really just the union of all the orbits. You see that? Yeah? Because you're taking each point and you're iterating backwards and forth. So this is equal to 1, okay? And then by the countable additivity, this is equal to the sum of the Lebesgue measure of Fn of E and in Z, okay? But this is equal to the sum for n in Z of the Lebesgue measure of E. Because the Lebesgue measure of Fn of E, by what we just said, is equal to the Lebesgue measure of E. And this leads to a contradiction, right? Because we have two choices. Either the Lebesgue measure of E is 0, in which case the sum is 0, but then this contradicts the fact that this is equal to 1, so it contradicts the countable additivity. Or the Lebesgue measure of E is positive, but then you have an infinite sum. This is always the same point, so this sum will become infinite, which again gives a contradiction with 1. Okay? So that's good if you've seen this example already, but I just wanted to review it just to motivate, again, as part of the fundamental idea, is that in general, this shows that this cannot be, we cannot take the Lebesgue measure and we cannot apply it in a consistent way to have countable additivity and to have and to have it defined on all subsets. You need to sacrifice one thing or the other. Okay. Okay, so since you seem to be fairly familiar, so maybe I will send you some notes, and if you're missing, for those of you who are missing some background, you can look. There's an appendix at the end of the notes which goes through several of the details of the measure, okay, and some measure theory. But the fundamental idea is one, that in general you need to define a sigma algebra of subsets. So if okay, so there's a couple of fundamental results though, is that so if a hat is an algebra of subsets, this means the same as a sigma algebra, but just for finite unions and finite intersections, right? And mu hat is finitely additive on a hat, okay? So then mu hat extends uniquely to the sigma to a countably additive, to a probability, to a measure, okay, to a countably additive measure on the sigma algebra generated, the sigma algebra A generated by A hat. So this is sometimes called the extension theorem, and it's very important because in general it means that basically the measure is completely defined by its values on an algebra. Okay? So example, take our space to be the interval 0, 1, or the real line, for example, okay? And let a hat equals the collection of all finite unions of intervals. Open or closed intervals, it doesn't matter. So you take any finite collection of intervals. This is an algebra of subsets, because if you take the finite union or finite intersection or complements of this, it's always finite unions of intervals. And we can define the length of these intervals, right? Let mu hat of a hat equals total length of A. Okay, a hat belongs to a hat. So if I take a set inside here, this is just a finite union of intervals, so I can take its length. Okay, and then the extension mu is called Lebesgue measure. Okay, so Lebesgue measure is exactly the extension using this theorem here. It's the unique measure that coincides with the length of any interval. Right? So you start with saying, okay, I take all the finite unions of intervals, and now I have an easy way to define the length of these intervals. Okay? And then by this theorem, this extends to a countably additive function, which is called Lebesgue measure. Do you know an example of a set with positive Lebesgue measure that does not contain any intervals? The Cantor set. Which Cantor set?
General. We can take one over 3, just we can take 1/4 or something.
Well, right, so the general counter set has 0 Lebesgue measure. If you take the 1/3 counter set, so when you take the construction of the counter set, you start by removing an open interval here. Let's call this U1. And then you have 2 connected components. And then you start removing here U2. And then U3. And so on. And so you write counter set is equal to the interval 0, 1 minus this union of all these UIs. Okay? And the topological structure of the counter set in this contains no intervals. It's the same as we did before, right? We did this example before. It contains no intervals, this contains no intervals. But what is the Lebesgue measure of this set? So by the properties of measure, we have that the Lebesgue measure of C is equal to 1 minus the Lebesgue measure of this union. Right? And because these are all disjoint, this is 1 minus the sum of the Lebesgue measures of UIs. Okay? So when you do the middle third counter set, this will be 1. This, because you cut out 1/3, you can do the calculation, you cut out 1/3, then here you count out 1/9 plus 1/9, anyway, you can add them all up, and you see that it gives exactly 1. But we can choose, we don't need to do 1/3. So we can take UI and U1, U2 smaller and smaller and smaller, right? So we can choose UI such that the Lebesgue measure of UI is equal to, for example, some delta divided 2 to the I. Sorry?
Yes, that each time.
2 to the I, and so this sum will be, so the sum of the Lebesgue measure of UI will be equal to the sum of delta 2 to the I, which is equal to delta times the sum of 1 over 2 to the I, and this is finite because this converges, so if you take delta sufficiently small, this will be less than 1. It can be made arbitrarily small. Okay? So this is very interesting. This shows that you can find a set, that there exists a set here which has no intervals, but its measure can be arbitrarily close to 1. Okay, because we can take this, we can start with this delta as small as we want, so we start with something that is a tiny size, and we take that tiny UIs. Topologically, we still end up taking all open, removing everything what's left has no open sets, but it still has measure. Okay, this is for me the most fundamental motivation for why we need to go from length to Lebesgue measure. Okay, because there's very natural examples of sets that don't contain any length. So this for me is the philosophical reason, why not philosophical, also practical reason why the difference between length and Lebesgue measure, right? Because Lebesgue measure can give meaning to the measure of sets that contain no intervals and therefore have no length. Okay, it's the formalization exactly of this point. So I think this is a very nice example to realize that it's not just trivial. This step here, where you have mu hat is finitely additive on a set of finite unions of intervals, it's very easy to define a measure on the sets, but it's not at all obvious what happens when you extend to the sigma algebra, right? It's clear that this C is part of the sigma algebra, so this so this is sometimes called the Borel sigma algebra, right? So A is called the Borel sigma algebra. Okay? So because it is the sigma algebra generated by the finite unions of intervals, you can more generally define it in a general metric space. And so one thing is to start with a finite set of open subsets, and to define this finite union as just some measure of these finite unions. And another thing is when you kind of go to the extension of the Borel sigma algebra, you really get many more complicated sets that you're now able to formally define what the measure of these sets are.
When we define the Borel sigma algebra, I think we define it as the smallest sigma algebra containing the open sets.
That's right. That's what I mean when I say generated. That's what I mean by generated is the smallest sigma algebra that contains this.
Okay. I thought it's...
Yes, thank you. Yes. Generated is because basically you can get it by taking all the countable unions and intersections of that, and you get the smallest sigma algebra that has to contain that. Okay, anyway, I'm very glad that you seem to have the fundamentals in place. So how is this all related to the dynamics? How do we associate this with dynamics? So our fundamental and first definition is the following. So let's suppose we have a map. So a lot of these definitions will work in general for measure spaces, but for simplicity, let's always assume that X is a metric space. And we will always assume that B, so usually I use the B, is the Borel sigma algebra. Okay, because we don't want to get involved with real technicalities about whether we have Borel or whatever. A lot of these things work for general measure spaces. And then we have mu is a probability measure, Borel probability measure. By this we mean that it is a probability measure defined on this Borel sigma algebra. Okay, so unless I say otherwise, this will always be the case. I will always assume that we are in this setting here. And then we have, let F be a measurable map. Here we really don't need map to be continuous, so you know what the measurable map is? The pre-image of any measurable set is measurable. So the pre-image of any set in the Borel sigma algebra is Borel. Okay, it's also in the Borel sigma algebra. And then we define the following definition. So mu is F invariant if mu F minus 1 is equal to mu for all A in the Borel sigma. So this says that if we have our space X here, and we take any set A, and then we look at the pre-image of A, then these two sets have the same measure. So this is a fundamental connection between the measure and the map, right? It's something that is stating a relation between the two. Here, when we write it like this, we put the emphasis on the fact that we're choosing a measure for a given map. But sometimes you can say, let F be a measure preserving map if you've already got a measure, right? So it doesn't matter, they're the same thing. In this case, we also say that F preserves the measure mu. Okay? Really, this is a relation between mu and F. And it turns out to have an incredible number of implications when you have an invariant measure.
Sorry.
Yes?
So a measurable function is a function that was the inverse of a measurable set is measurable.
Exactly.
Not Borel.
Well, Borel is Borel. Let's say Borel measurable. So the inverse of a Borel set is a Borel set. The pre-image. So if you take a Borel set here and you look at the set of points that map to that, then that's also a Borel set. is like a generalization of continuity. When you have two topological spaces, you can define continuity without use of a metric, right? So if you have metric spaces, you can define a continuous function with epsilon and deltas. I think you must have done in topology. If you have two topological spaces, so no metric, you can define a continuous function because a topology has the sets that belong to the topology. If the pre-image of a set in that topology also belongs to that topology. Have you done this? Yes? So this is just the generalization. You have a set, you have a sigma algebra here, and you say this is measured with the pre-image of every set in the sigma algebra also belongs to the sigma algebra.
So the measure is restricted to the Borel sigma algebra.
That's what a measure is. Yes, a measure is always restricted to the sigma algebra. In this case, we will always restrict to the Borel sigma algebra.
Because in the case of the real numbers, we had measurable sets which were not Borel.
You're right, but they all have measure 0. So you're right. We could get into the technicalities of this. Let's pretend we don't really care about this. They all have measure 0. And as you will see, we don't care so much about measure 0. But you're right, you can be a little bit more sophisticated and say that in some cases we want to consider also the measurable sets that are not Borel, but it will not be, in our setting, this will not matter so much, okay? But strictly speaking, you're right. Yeah. So you take the Borel sigma algebra and then you add all the sets that have measure 0, and you get all the measurable sets. In practice also, we will always have X to be at least continuous, or continuous with just a finite number of discontinuities, and then it will be automatically measurable. Okay, so I'm just doing this, writing this because strictly speaking for the definition, you don't need anything more than just measurability of the set. So let's see some examples. Obviously, first of all, so example 1, let's suppose S1 plus 1 is a rotation. F of x equals x plus alpha. Mod 1. What invariant measure do we have here? So I've not actually discussed any other measures except the Lebesgue measure. Have you done any examples of other measures that are not Lebesgue measure? Just Hausdorff measure.
No, we didn't do the Hausdorff.
No, we.
The other examples were the trivial ones.
Trivial means what?
And like the set of all sets, one which is the measure of a set is infinite. And not
Okay. So we will.
In real life, we have seen Hausdorff measure just one lecture, and we.
I see. Okay, anyway, for the moment, for our case, there will be mainly two measures that will be important. One is the Lebesgue measure, okay? In this particular case, you see that Lebesgue measure is invariant. Lebesgue is invariant, right? Because this is just a translation. So again, Lebesgue measure is invariant by translation. That's exactly what it means. So you take a set here, A, right? And you look at its pre-image. So this is A, this is F minus 1 of A, and it's just a translation and the length. So one of the ways in which we're going to use the extension theorem that I said before, which is going to be very useful, is that to check invariance, you only need to check invariance on the algebra of intervals, basically, in a one-dimensional setting. Because it's not completely trivial and I'm not going to prove it, but if you check the invariance property on this algebra, then it automatically extends to the invariance property on the sigma algebra that's generated by that. Okay? So we will use this in practice when we want to show, for example, in this case that Lebesgue is invariant. You already know from the general theory that Lebesgue measure is translation invariant, but even if you didn't know that, then it's obvious that it's invariant for intervals, right? Because if you take an interval A and you translate it, it has exactly the same length, and then using this consequence of the extension theorem, it follows that it's invariant on the sigma algebra, so it's invariant overall. Okay, then we have some other measures here, that are invariant in some cases, which come from the following example. Let me write it. Suppose we have a fixed point equals P, okay? And now let delta of P is called the Dirac delta on P, and this is defined in the following way. This is 0 if P does not belong to A, and 1 if P belongs to A. This is called the Dirac delta measure on P. Okay, so the way to visualize this is that we have our space X, we have the point P, okay, and all the measure is concentrated just on the point P. So the way I like to visualize a probability measure is like having 1 kilogram of sugar, okay, and you just distribute this 1 kilogram on your space wherever you want, right? So it's not obviously a correct, accurate analogy, but in some sense Lebesgue measure corresponds to spreading it out as uniformly as you can, whereas here I decide to put all my kilogram of sugar just on the point P, okay? And so then you take a set A, okay? If it does not contain the point P, it has measure 0. If it contains the point P, then it has measure 1. That is called the Dirac delta measure, and you can easily check that it's a measure in the sense of the definition we had before. Now, is this invariant?
Yes.
Why?
Because any set which because P is fixed and each set with the P image of a set that contains P will contain P.
Exactly. Exactly. Okay, so I will leave that for you to check exactly, but Dirac delta on P is invariant. Is F invariant? So the Dirac delta you can define on any point, clearly, but it's only invariant if P is a fixed point. Okay. So for example, suppose here that we get alpha, suppose the identity map on S1, for example. Then you have several invariant measures because every point is a fixed point. Okay? So on every point we have the Dirac delta measure on X is an invariant measure. So there's an uncountable number of invariant measures. Plus Lebesgue measure is also invariant clearly for this. In fact, for the identity map, every measure is invariant. Because F minus 1 over A is equal to A. Always. Okay? So every probability measure. This shows that the invariant measures may be lots of invariant measures in the system. Okay? So for the identity map, every measure is invariant. What if we have a periodic orbit? P1, Pn, periodic. So suppose we have P1 goes to P2, goes to P3, goes back to P1.
Then it's Fn invariant.
What is Fn invariant? What measure? Dirac delta P1. Yes, so can you use that observation to construct a measure that is invariant for F? What do we need now?
Divide the measure.
Split it up. Yes, split up the measure. So let's put 1/3 of the sugar here, 1/3 here, and 1/3 here. Right? So let's define a measure mu equal to 1/3 delta P1 plus 1/3 delta P2 plus 1/3. Okay, sorry, let me write it in the general case. So mu is equal to 1 over n, the sum of the Dirac deltas into R. So I will leave it to you to check that this is F invariant. But what if we didn't split it up uniformly? What if you put say 1/2 mu is equal to 1/2 in delta P1 plus 1/4 in delta P2 plus 1/4 in delta P3. So this is still a probability measure, but instead of splitting it up equally, I put a lot more in P1 and less in P2 and P3. Is that going to be an invariant measure?
No.
Why not?
We can take a set, for example, what set is just contains one of the P.
Exactly, right? So you can take here, in this set you can take A equal to be just the point P1, and then the measure of P1 is 1/4, but the pre-image will not contain P1, it will contain P3, and then it may contain other points but outside. The only other point, because this map might not be invertible, right? It may contain other points, but these points will have measure 0, so the image of F minus 1 of that will be 1/4. Yeah, so it's cannot invariant. Okay? So this is invariant if and only if you spread it evenly, which kind of makes sense. Right? That's what you do. So let's see if there's any other relevant. I was forgetting the best, which is our example. Our favorite example. What's our favorite map? Fx equals 10x mod 1. Example is 4, 5. Okay. So remember the graph of this map. Well, first of all, you know that this map has some fixed points and some periodic points, right? So every one of those fixed and periodic points, you can put those invariant measures on them, right? So already there's an infinite number of invariant measures that we already know that are sitting on the fixed points and the periodic points, okay, all coexisting. What about Lebesgue measure?
No, it's not.
It's not invariant. Let's take an interval here, A, and let's look at F minus 1 of A. It's the union of little intervals here, right? So there will be one little interval here that maps to A. There will be another little interval here. So I did not draw the picture very well, just to confuse you. How many intervals will we have? 10. And what is the length of each one?
A over 10.
1 over 10. A over 10, sorry. 1/10 of A. So what's the measure of the union?
It's the measure of A.
Yeah.
It's here.
Yes. Yes. So again, we use the observation I said, which is that it's enough to check it for intervals. And so this implies that it's true for every Borel set. And so this implies that the Lebesgue measure is F invariant. And the same also obviously for 2x mod 1, 3x mod 1 is the same, right? If you have 2x mod 1, then what's the situation here? You have A, and you have how many? The pre-image has two components, and each one is 1/2. Okay, so the big measure is also invariant here. You can easily do 3x mod 1, 4x mod 1, it's all exactly the same calculation. The big measure and all the fixed points and periodic points. We will see that there's also many more measures, invariant measures.
It's related with the conjugation.
You can use the symbolic dynamics to also study some of these measures. No, it's not so much related to the conjugation class. I mean, in some sense, now we're going to use the conjugacy to construct more measures. We will get that. Okay, at the moment I don't want to talk about that so much. But let me just say one more thing. I would give an exercise, which is a very useful exercise, which you can already do now. But first, let's look at a simple example. What if these two branches are like this? Is Lebesgue measure still invariant now?
We have to construct like the delta looks like this maybe. I mean, we have to do like this.
So you don't think Lebesgue measure will be invariant? We need to construct a new measure.
We need to construct it using y Lebesgue measure.
Are these
Not
lines?
These are straight lines, yes, straight lines. Yes, that's a crucial point. These are straight lines. So suppose this point is the point S. I'm going to leave it as an exercise.
Okay.
I'm going to leave it as an exercise. Not only I'm going to leave it, this is one of the main exercises. I think it should be here. Okay? So, not only exercise 19, it's in here. So, not only is Lebesgue measure invariant here, okay? If you take any, so you can have several of these, it doesn't matter. How many branches you've got, the Lebesgue measure is invariant, even if you have an infinite number of branches. Okay, that's when the exercise gets a little bit tricky. So exercise, suppose f 01 to 01 is a piecewise affine full branch map. Okay, this is exactly the class of maps that we studied at the end of the first part of the course. Okay, then, even with, let me add this, possibly with a countable number of branches.
I have a very compelling argument.
Just a second. Possibly with a countable number of branches, okay, then the Lebesgue measure is F invariant. Yes.
If I say what I'm going to say, it's going to solve it.
Okay, say it. So we're all solved.
So it all depends on the reciprocals of the tangents all add up to 1. So the tangent of each line, the reciprocals will add to 1.
Exactly.
So that's
Exactly. Okay? So if you understand what he said, then you can use that to solve the problem faster. Otherwise, you will get there anyway. That's exactly the point. It's because the reciprocal of the tangents gives you the ratio between this and the size of the pre-image, and so you can easily, for this case, you can do it by hand. So you can really, because you know S, then you know the slope here, and you know the slope here. This is 1 minus S, and then you can calculate the ratio between this size and this size, this size and this size, and you see they add up. But to extend it to a countable number, you need exactly that observation. Okay, I will let you think about it. What if they're not piecewise affine? Right, so what if
Balance.
Okay? Then of course in general a Lebesgue measure will not be invariant. Because there's no way, so the size you cannot control. If you do not know exactly the shape of these curves, then you cannot control. If you take something, a set of size A here, its pre-image will depend. For example, this part could be very flat here, and then it could get very steep, and then it could be very flat here. So if you take a set here, its pre-image will be very big. Okay, whereas if you take it here, its pre-image will be relatively slow, so it can change. Okay, so we will address this towards the end of the course. We will look at, if you remember, even when we studied the topological conjugacy, at some point I said, actually, you don't need these maps to be piecewise affine, you just need them to be expanded. Remember, I said you just need the derivative to be bigger than 1 for the whole argument of the topological conjugacy to go through. So here also we will generalize the situation, and we will see that under some conditions that are not piecewise affine, we will still get another measure that is not Lebesgue measure, but is absolutely continuous, is equivalent to Lebesgue measure. Okay, but now I'm just saying what we're going to do later. For the moment, we will just stick with the piecewise affine case.
But can there exist some curve for which the Lebesgue measure is invariant, other than the straight line?
That's a good question. I don't think so. If you have two and they exactly match each other, maybe they cancel each other out exactly. That's a good question. I haven't thought about it. If Lebesgue measure is invariant, does it mean that it's piecewise affine? I'm not sure. You would have to have one branch having a certain slope, and then the other one must exactly compensate. So where this one is a little bit bigger, that one's a bit small, maybe. Anyway, so the question really is, so what? Okay? So why are we interested in invariant measures? So all I've done is given you some examples of systems that have a whole bunch of invariant measures. And so what? So the first person, as far as I know, to realize the significance of invariant measure was Poincaré. And he proved what is now called as the Poincaré recurrence theorem. And it's the following. So we have f x to x, again measurable. Mu is an invariant probability. Let A in X be a subset that has positive measure. Then the amazing thing we have is, with no information about the kind of dynamics that this is, we already know then for mu almost every x in A, so you know what mu almost every means, right? It means that there's the set of points for which what I'm going to say does not occur, has just zero measure. So almost every point x in A, there exists some tau x greater than 0 such that f tau of x belongs to A. Tau of x. So this is saying that if you have a set with positive measure, essentially every point comes back to A. And this is the so recurrence is going to be the key word throughout this section, in the sense that recurrence is what makes interesting stuff happen, right? if you think about the examples that we've looked at, the first two classes of examples, we did not have much recurrence. In the interval diffeomorphism, everything converges to a fixed point. Okay? By recurrence, we mean basically that, points coming back close to each other. Okay? And even in the local contracting maps, we just had contracting maps where everything just went to the fixed point. Okay? In the third class of examples, the full branch piecewise affine or piecewise expanding map, that's when we start to have much more interesting and much more rich dynamics. We have all these periodic points, we have all these dense orbits, we have recurrence because points are coming back somehow. Okay? So those in some sense are where it's interesting. And so you can easily verify it in let's just look at a couple of examples. So, example, if we have a periodic point, okay, P1 to Pn periodic point, let's just check the Poincaré recurrence theorem in this case. Does it work? So then we have, as we said, we have the measure 1 over n. So we have the Dirac Delta here, right? So is that true? So let's take a set A of positive measure. What does it mean that A has positive measure for this measure here?
It contains at least one of the...
Exactly. It must contain some point. Okay? And so does this point come back?
Yeah, of course.
Because it's periodic, so it comes back. Okay? Remember that this is a kind of essential bit, right? This is in some sense what makes the magic not so magical, because in this particular, this theorem, as we shall see, many of these theorems that we shall prove, they're very powerful, but they really are looking at the system with the glasses of a particular measure that you've chosen, right? So in this case, we've chosen this particular measure, and this measure only sees the points of the periodic orbit. Everything else has zero measure. Okay? So when we apply this theorem, okay, it's right. It tells us that this point comes back, but of course there may be loads of other points of which we know nothing about, whether they come back or not. But it doesn't matter, because when we say mu almost every point, it means that the set of points for which we are not claiming that this is true has zero measure. And in our case, this is the measure we chose, so everything else except these points here have zero measure, so we don't know and we don't care. Or maybe we care, but there's nothing we can do about it. We don't know what happens for those points. Okay, because these are the points. Of course, if you have 5 points, if this is a periodic point of period 1 million, and we have 5 or 2,000 points in here, then this will apply to all of those 2,000 points. All of those 2,000 points will come back, which corresponds obviously because they're part of the same periodic orbit, so they will all eventually come back. Okay. What about 10x mod 1? So fx equals 10x mod 1. Right. So let's take some tiny small interval here, a positive Lebesgue measure. So let's suppose mu is equal to a Lebesgue measure. So is it true that almost every point comes back to this set A? Why? Well, just to get a feeling for it, of course, if we choose, let's choose this, for example, as the set of, let's choose this in a particular way, like 0.53 to 7 to 0.538, for example. Right? So all the points in here are exactly the points whose decimal expansion starts with 0.537. Right? Now, almost every point will have, in fact, this is something we will, well, this is a consequence of this, but intuitively, almost every point in here, at infinitely many times, you will find the sequence 537 in its decimal expansion. Okay? And because you find this sequence 537, then every time you find it, remember when you iterate, it's just shifting the decimal expansion. Every time you find 537 in it, you take a point here, almost every point 537 will occur infinitely many times, and so it will come back here. This is actually a consequence. In some sense, it's not a verification. It's an example of the fact that this Poincare recurrence theorem guarantees that almost every point in here has the sequence 537 occurring infinitely many times in its decimal expansion. Yeah, so it's a non-trivial fact. So I shouldn't have said that it's a way of checking this. It is just an observation that as a consequence of this, we have a statement about the decimal expansions of these numbers. Okay, so this is really helpful as a nice example of why this is interesting. It has, in fact, applications beyond dynamics. In fact, Poincare recurrence is used in many different settings. It's kind of also behind this. Physicists often talk about whether the universe has Poincare recurrence, right? There's this famous, in statistical mechanics, there's this famous example of when you take a box and one half of the box is full of gas molecules and the other half is vacuum, right? And then you lift this so that the gas spreads in the whole box, and then you say, okay, what is the configuration? If you think of this as a dynamical system, what is the configuration of all this? Will it ever, if you wait long enough, will it come back to its close to its original state? Okay, because this is what it is. It's taking a small set and it's taking at almost every point comes back to this original state. Right? So will you ever get this box where 99% of the gas molecules are in the first half, because you started off with a situation where 100% are there, right? Will you ever have this Poincare recurrence? So do you have? So this is a question that is asked in many physical and natural systems. You know, do you come back to close to your original state?
So does it come back?
This, I think, the jury's still out on that. I don't think the physicists can prove things as well as mathematicians do. But they set the problem. So let's prove Poincare recurrence theory. It's very simple proof, actually. So let's define A0 equals a set of x in A which do not come back. So we have our set A here. So we just need to show that this set has zero measure. Okay. So let also An equal to F minus N of A. Okay. So claim is that for all n greater or equal to 0 with n different from m, okay, this implies that An and Am are disjoint. In fact, let me leave that as an exercise. It's a simple exercise.
They have the same measure?
Sorry?
They have the same measure?
Yes, this is what we're going to use now. This does not depend on that. This is just a set theoretic thing. Okay, because you can see, I will leave it as an exercise because I'd like you to do it, but you can easily see that if they were not disjoint, if there was some point here, then it would imply this point would come back.
This is A0 one or just An?
So all these sets, we now have a collection of sets. An, n equals 0 to infinity, yes? They're all disjoint. This is the statement. Maybe I should have just said it like that. So you take A inside A0.
They don't contain A0, but maybe it's not this.
Okay. I don't know whether I should do it or not. I'm just going to let you do it as an exercise, okay? It's not that difficult. You want me to do it now, or you want to do it as an exercise? You want me to do it?
I think it's
Finish the proof?
No, just to do this exercise here. You can do it, okay? So let's see what that means. So then, sorry?
Otherwise, it's point.
You mean why you get this? No, because otherwise you see that this point comes back. You see, well, I'll just do it as an exercise, okay? Okay. So what are we going to do with this? Then it's very easy. Then we have by the invariance of mu. For this, it does not need the invariance. This is just the fact that these points do not come back. It implies this, right? By the invariance of mu. By the invariance of mu, we have that mu, they all have the same measure, as you said, right? Is equal to A0. Okay? And therefore, we have the mu of the union of AN is equal to the sum of the unions of AN. And this is similar to the calculation before. This is the sum, n equals 0 to infinity. This is where we use the invariance of the measure. Right? This is mu over 0. Okay, so what are the possibilities here for this sum? So you see, we take the union of AN, but because they're disjoint, okay, we use crucially this thing, then we can write this as the measure of all the mu n's, but because of the invariance of the measure, each of these mu n's is just equal to the measure of A0. Because I forgot to say that, but it's an obvious consequence. The definition of invariance says that f minus 1 of A has the same measure as A, but clearly that continues to hold on the iteration, right? So that implies that f minus 2 of A also has the same measure f minus 3 of A. So it's an immediate consequence of the definition that f minus n of A has the same measure of A. So what are the possibilities here? If mu A of 0 is equal to 0, then it's okay. This is 0, and that's okay because that's what we're trying to prove, right? But what if mu A of 0 is positive? Then this is infinity. And can this be infinity?
No, it's probably infinity.
No, because this is obviously less than or equal to the measure of the whole space, which is equal to 1. And this therefore implies, this is a contradiction. Well, no, this is not a contradiction. This just implies that mu of A0 equals 0.
Sorry, I think there should be A0. AN equal to F minus n A0.
Sorry, is that what you said before? I'm so sorry. I'm so sorry, obviously, yes. I did not realize that's what you meant to say. Yes, yes, yes. Yes, of course. Okay? So this is Poincaré recurrence. I think that probably he proved it for the volume, right? I don't think he proved it in general for general invariant probability measure. I think he proved it for systems that preserve the area or the volume, right? Area preserving, volume preserving. but the proof is exactly the same for general invariant probability measures. So this shows that somehow you get recurrence, right, with respect to that measure, to some measure. What it does not tell you is how many times it comes back. So we leave it also as an exercise that in fact mu almost every x returns to A infinitely many times. Which is you need a slightly more sophisticated. It's in the notes if you want to look, but you can probably work it out yourself. But it's not an immediate consequence. So this shows that almost every point comes back once, right? It's not completely obvious that when they come back, then they come back and they belong to the set of points that also comes back. So you cannot just iterate this. You need to do a slightly more sophisticated construction, but of the same kind here. Okay. But we want to be even more sophisticated, right? We would like to know how many times it comes back. Okay, how often it comes back. And this Poincaré recurrence thing goes back to the 1890s, so even to the 19th century. And then we have, in the 1930s, this quite remarkable theorem of Birkhoff, which I'm not actually going to prove, but let me state it. So theorem, and this is the theorem that is due to Birkhoff in the 1930s, actually 1931. So these are very classical results here. And it says the following. So again, we always have the same setup, fx to x, mu is an f invariant probability. So now let f be in L1 of mu. So you know what L1 mu is? Yeah, integrable, mu integrable functions. Then the limit, sorry, not f, phi. Phi is a function. Phi, right? So phi is a function from x to r, right? Suppose it's an integrable function. Okay. Then the quantity, the function phi x of f, which is by definition the limit as n tends to infinity of 1 over n sum k equals 0 n minus 1 of phi composed with fi of x exists for mu almost every x. So the easiest way to think about this is to take as an example let A be some subset of x and let phi equals the characteristic function of A. Then let's look at what this means. Right? Okay, then what does this mean? Then 1 over n of the sum k equals 0 to n minus 1 of the characteristic function of A composed with the fi of x. What is this doing?
It counts the number of times x is in A.
Exactly.
Is that like an expected value or something?
We will see. We will see. Okay, more or less that's what it's saying, is that the expected value exists. Okay, because this is counting, so this is here, this is our space X, this is our set A, right? And then we have our function phi, which in this case is equal to the characteristic function of A. So you take a certain point X, right? And then you look when let's put K here. So when K is equal to 0, this is just a characteristic function of A in X. So it's either 0, 1, depending on whether X belongs to A. And then for each K, you look at Fk of X and you decide whether it belongs to A, and you get 0, 1 here. Okay, so you're counting, and then you're taking 1 over N. So you're taking the average number of times. You look at the orbit of X, and every time it falls in A, you're adding 1. So this, we can write like this as 1 over N times the cardinality of the set of indexes K between 0 and N minus 1, okay, such that Fk of X belongs to A. Okay, so as you said, it's just counting how many values of K this happens. Okay, what this says
Weighted out anyway.
is that the limit converges. Sorry?
For phi general,
Yeah, for phi general is the same thing. It's you're taking a general phi, okay, and what this is doing is just looking at the average value of phi along the orbit. Okay, so phi is a more general L1 function. At each point along the orbit, you look at phi in phi k of x. Okay, now this is just an L1 function, so it can be very wild. Okay, and you just take this is the average value of phi along the orbit. Okay, now there is absolutely no reason why this should converge. Okay, and in general it does not converge. Why should it converge? Phi has in some sense a certain, perhaps it says a certain average value, whatever, but you look at, take an orbit, why should the orbit of X exactly kind of visit different regions of the space in such a way that it picks up exactly some kind of average value? Okay, the best, easiest way is to look at this, right? The number of visits. So what does it mean to converge? It means that if you maybe initially the point X would stay outside A for a long time, but then it enters A, and maybe if you look at the first 1,000 intlets, you see that it spends about 10% of the time in A. Okay? And then you say, okay, it's looking like it's spending 10% of the time in A. Then you wait longer, and then maybe actually now, this time it stays outside for much, much longer. And you say, okay, I was wrong. Actually, this is going down. Now it's looking like it's spending only 5% of the time in A, right? And then at some point I fall in here, maybe there's a fixed point, I come very close to this fixed point, and I spend lots of time in A, and if I wait for another 1 million intlets, oh my gosh, actually now, from the beginning till now it looks like I'm spending 90% of my time in A. You don't know. The dynamics may be whatever. Okay? But for mu, again, of course, this is going to be very important. This is not for every point, because there's lots of exceptional points. But for mu and almost every point, this limit converges. This is really the fundamental. This is you can see there's a quantitative, very sophisticated quantitative improvement on Poincare recurrence in some sense. And this really is magical, actually. This existence of the limit is...
Limit is smaller than integral.
Excuse me?
Limit is for every x, limit is smaller than integral of phi.
Yes. So what we're going to show, I don't know if next lecture or the one after, we're going to talk about ergodic measures. Okay. And this is an additional property. If a measure is both invariant and ergodic, then we know also what this limit is. Okay? And if the measure is ergodic, this is just the integral of phi with respect to that measure. Which is actually the average value of phi in some sense with respect to that measure. Right? There's an obvious way to calculate the average value of phi. If you have a measure, you just integrate phi with respect to that measure. That is, in some sense, the average value of phi. Right? And so it is a natural question whether this converges to the average value of phi, and of course it depends on where this orbit is going, and it turns out that if the measure is ergodic, then it converges exactly to that. So ergodicity will be the main focus, okay, once we develop that additional property. Okay? So often, most of the times, this is part of what's called Birkhoff's ergodic theorem that contains the second. Usually the theorem is stated for invariant ergodic probability measures, and it contains also the statement that this is equal to the integral of phi. But I wanted to separate these two because I think it's often lost that the ergodicity is a kind of secondary thing. The existence of the limit does not require ergodicity, it just requires the invariance, and I think it's very useful to know that. Okay? The proofs, there are so many proofs of Birkhoff's of this theorem. None of them, unfortunately, really help to understand why it's true. So it's a very technical proof. It is in the notes. One proof is in the notes, but I've decided I'm not going to give the proof, and I'm not going to require it in the exam either, because I think it's a technical proof that it's useful to go through, one of the many proofs if you feel like it, but I think it does not really add much to our understanding, really, of exactly why this is true. So I think we will, for the sake of this course, we will skip it. Okay, and instead I want to we'll complete at the next class, but let me say something about the existence of invariant measures. So far we have seen we've seen the definition, a bunch of examples, two theorems, the Poincare recurrence and Birkhoff's theorem about invariant measures, but do we know whether they exist in general? If I just give you a dynamical system, if you have periodic orbits or fixed points, then you must have at least some invariant measures. And what if it doesn't? Do we always have invariant measures? So this is the content of the next theorem, which I will finish proving the next time, which we'll prove in the next lecture. That is so theorem. This is sometimes called Krylov Pogulyubov. I'm not sure if I'm pronouncing it the right way. Anyway, Krylov-Pogulyubov theorem. This is also from the 1930s, I think. I'm not sure. And it's if X is a compact metric space, and F X to X is continuous, then there exists mu F invariant probability measure. There exists probability measure mu, which is F invariant. So we prove this because it introduces also some interesting techniques. Let me just spend the last few minutes here looking at some counter examples. Okay? Let's look at some examples if we relax some of these conditions like compactness or continuity that we may not have invariant measures, right? So suppose X equals the open interval 0, 1. And let F of X equals 1/2 X. Then what is the dynamics here? Why do we not have any invariant measures? How can I prove? Well, first of all, why intuitively do we not have any invariant measures, and how do we prove that we don't have invariant measures?
Because it's going to explode.
So everything is going to 0, right? So the fixed point is not included, otherwise we'd have an invariant measure, which is the Dirac Delta on the fixed point, right? But we know that everything Fn of x is converging to 0 as n tends to infinity. So you take every point here and it's converging to 0. Why does that imply that we cannot have an invariant measure?
Because there is a set which
If we take both,
it escapes from
Yes.
this set.
Yes.
At this point, for instance, an interval.
Yes.
If you take an interval here, and it will escape at infinity.
And so?
And so the measure of the events, well,
If we
Wait, you were saying something?
If you take a whole set and its measure is 1. I mean, if we talk about whole set X,
Yes.
it's 1. The value of one side is 1, but other is like it's converts to 0.
What we need to show is that there cannot be an invariant measure here.
Yeah, it's not invariant in this case.
Well, that measure might not be invariant, but how do you know that it does not exist any invariant measure? That's what you need to show, that it does not exist. I'm not saying that Lebesgue measure is clearly not invariant, because if you take something of a certain length, it shrinks to half the size. So Lebesgue measure is clearly not invariant. But as we said, there's other invariant measures. There's invariant measures on fixed point, there's invariant measures on periodic orbits, there might be other invariant measures that we don't know of. But there is a completely abstract argument, yes.
So I think the argument is if we take an interval and make it into half, it goes to 0. So we would like the mass to be concentrated at 0, but 0 is not there.
Intuitively, we would like the measure to be concentrated at 0, but this is not there. But this does not prove that
It's
maybe
not-
our intuition.
Can we
maybe
look
other
at
invariant
0,
measures.
1, 0, 1, 0, 1, 0, 1 has the same measure as 0 to 1 half. Assuming for contradiction it is true. Then 0, 1 has the same measure as 0, 1 half, and 0 to 1 fourth, and so on. But this measure has to be 1. So.
Wait, what is your suggestion?
maybe we can construct a contradiction to Poincare convention or something.
Yeah. How?
For example, if we take any interval, so in this case, if we take any interval, if we take one point in this interval, is iteration going to 0. This will never come back to.
It will never come back. That's the easiest way, okay? If there was an invariant measure, then you would have somewhere a set of positive measure, yes? And by Poincare recurrence, almost every point would have to come back to that set. But this is not possible because these sets, the points, once they leave, they never come back.
Also, we can take a proper subset, any proper subset, assume we have a proper subset which has, or a proper interval which has positive measure.
Yes.
Then we could shrink the interval of 0, 1 inside that set. So,
What you should add after that is, suppose you take an interval that has positive measure,
yes.
but you can construct this interval so that it never comes back, just like it's saying, right? So somewhere there must be an interval that does not contain 0 that has positive measure, right? If you have an invariant measure, it's an invariant probability measure, so you need to be able to find some interval here that has positive measure, right? And you can take it very small so that the image of this interval maps outside here and it never comes back. And so that contradicts Poincare recurrence. So Poincare recurrence is recurrence. So this is telling you, this is a way to remember that if you have invariant measures, you have recurrence. Okay, so one of the easiest ways to see that you do not have invariant measures is that you don't have recurrence. And of course, the point here of having this compact metric space and X continuous in some ways to avoid this kind of situation, because Here, if you close this, of course, you could not have that situation because you have that endpoint here. Right? So this is based on the fact that this space is not compact. What if the space is compact, but the function is not continuous? Can we construct an example also that doesn't have an invariant measure like this? We can actually do a very simple variation, basically the same example. So we can define it still to be 1/2 of x here. So we can define f of x to be 1/2 of x if x is greater than 0, and 1 if x is equal to 0. Okay, so here the image of 0, you put it at 1. So it's not continuous. And again, you're destroying the only possibility we had of having an invariant measure, which is if there was a fixed point here. Because everything now is still converging to 0, but 0 is no longer a fixed point. So if you put the Dirac Delta at 0, it's not going to be an invariant measure. Because 0 is not invariant. It goes to 1 and then it comes back. Yeah. And none of the other points come back. Right? They all just converge to 0. So these have no invariant measures. I think this is really the initial motivation introduction for invariant measures. We're going to prove this, and then we're going to start talking about which invariant measures we're really interested in. For example, ergodic measures. Okay, thank you very much.